How's it going, everyone? And welcome back. We're going to continue working on this power supply some more. So tonight we have to make the transformer component, and then we have to start working on, at that point we'll have our lower voltage, so then we'll have to start working on the full wave rectifier, which is just the diodes and everything. And then, yeah, at that point we'll be able to start working on DC stuff. I was thinking about this for the past couple days, and there might be some merit into making sure all the AC current stuff and that diode network is on a different circuit board than whatever we pick as the micro and all that logic and digital stuff, just to ease interference and make it less likely that we just completely torch something if we do this wrong. Because that high power stuff can absolutely just shred whatever DC electronics, the micro, the screens, and all the outputs and all that stuff if we don't take care of it. So separating them on boards is a common practice to keep them from causing each other issues. So there might be some merit there. Although I've seen a lot of power supplies where everything's kind of contained onto one board. So I don't know. We might just try it on one, and then if it fails spectacularly, we try it splitting it up, see what happens. But let's get into it. As usual, if you have any ideas or thoughts or things you want to talk about, just let me know. All right. Let me turn the music back on. All right, so last time we designed this, our power input. Next we need our transformer. And we are going with this one. For not any particular reason other than it seems like it's the right one. So. Chassis mount transformer. And we are not going to chassis mount it. Does it even give, like, circuit board connections? I don't think it does. That might be a problem, actually. Because we can figure out how to put something on a circuit board to just, like, drop it into, but it's the way it's designed is designed to be attached to the case of whatever it's in. So it may not be a good idea. Interesting. I think this is the problem I dealt with before too, because pretty much every transformer I found, you couldn't find many that were like PCB mountable, at least not intentionally. And I know we said we wanted this one because of its ratings, 2 amps output and 28 volts. Let's see. Let's see if there's any other options here. I know we spent all that time picking this one, but I didn't really think about that part. That we should get something that's intentionally supposed, like this is supposed to be on a circuit board. Obviously, this one's probably not very powerful. 20 volts. Let's see. In stock, active. Mounting type, surface mounted through hole. Lots of through hole options, so that's good. Maybe we can find something. Inputs are fine. Yeah, we just can't put out enough current with these. Oh, wait. What is this? This has got to be expensive, right? 4 amps, 2 amps. Not bad, actually. This might be exactly what we're looking for. So basically, it has two options for output, right? 14 volts or 28 volts. 14 if you use the if you use only one side of it. 28 if you use both, but you got to connect them in series. Interesting. And they're in stock and not too expensive. I'm hoping to get like a circuit diagram or something. Because I understand connecting these in series. I don't know about this side though. Oh, excuse me. Through hole. We're going to be really careful with that. If you pick up the circuit board, you could shock yourself if you touch it in the wrong spot. Primary voltage is 115 or 230. So if it's 115, you would connect it to each, and if it's 230, you would do a series connection, I believe. Hold on 2 seconds. Let me... Yeah, okay. Hold on. All right, so... where? Okay. I can't be the first one to have this question of how exactly this works. What I'm wanting to know is if I can connect 115 volts to each of these to get the desired result. Apologies for this. Thank you all for bearing with me. Okay, yeah. It looks like the way people are saying this, yeah, you connect the two of them in parallel. So that makes sense. Okay. So this is perfect, I think. Is there any way we can get a CAD model? Maybe? Ooh, that looks cool. That looks really cool, actually. Well, I really hope I get the pinout correct. I also have no idea how to draw a transformer symbol, and I'm going to have to do that. Unless I get super lucky and it just happens to be here as a part option. Alright. This off the side. This off to the side as well, so I know which one I am. Okay. M4A 5628. Let's try that. No model. That sucks. I didn't think we'd have one, but I was hoping to get lucky. Alright, so it looks like we're building one. I guess we'll just make a new symbol. Alright, this is going to be semi-tricky. But we have kind of a drawing here that works a little bit. Oh, maybe it has something. Please, 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 please. Oh, they're not alphabetized. Nothing. All right. Oh, wait. More symbols. Transformer. Okay, hold on. Go away. Let's try that again. Man, I wish I'd known this existed. There we go. All right, we'll drop that one there. And then we need a second one. come on. Urgh. I can do it. Oh my gosh. There, fine. All right. They give us a pretty good picture here. Tells you the pinout. 3, 4, 6. Which is just weird, actually, now that I'm looking at it. Designator. This is going to be 1. This is going to be 3. Whoops. Four. And 6. 7. 9. 10. 12. Okay. And then since it's a parallel transformer, we need 2 bars inside. I need a line. I guess this will work. There we go. And then one more. Oh. Navigation is weird in this. Okay. This should be 500. Okay. Excellent. All right, that's our transformer. At least our symbol. All right, let's make a footprint for this. This part's going to be a lot. Hopefully their model is pretty descriptive, because seeing how this whole thing lines up is going to be tricky. Interesting. All right, so which one are we looking at? Sorry, I'm gonna pull this up here. 14A5628. Oh, that's probably the power, the volt amps. So 14A56 and 28. What's the 28? Is that the output voltage? Oh, they have a 36 volt option if you're willing to go down in current. Interesting. All right, let's see. Oh, that's what I was looking for. I was trying to figure out the dimension of the pins, how far apart they were, like the two rows, but C is that. Okay. So we care about A, B, and C, really. I wish I had like a top-down view that was showing all the pins as well. Although I guess if we get this wrong, we just turn it around. And it should work just fine. Just get everything on the same side. All right. It also doesn't tell us how big to make the holes for the pins. Square PC terminals. Here's the square pin dimensions. 25 mils. Oh wait, 45 mils, because it's a sizable one. Yeah, we need to use this row here because we're doing the 56 power. 56, is that watts, volts times amps? I think so. Okay. All right, in that case, we need 8 vias, big enough for 45 mils. I guess we'll do 60. Try and give it a little clearance. We need the hole size to be 60. I can't shake the feeling that that's pretty close. And I feel like these should be sizable because they're going to have to carry a lot of current anyway. We'll see what it looks like when we pull in the 3D model, and if it looks too ridiculous, then we can always make it bigger. All right, so that looks good. I think designator to 1. Okay, so that means needs to go over half a C. .9, so whatever half of 1.9 is, so 0.95. So negative 950 mils. It's way out there. And it needs to go down to half of B plus A. So 15 plus 60, so 75 mils, so negative 75 mils. Right? No, negative 750. There we go. All right. One, two, three, four, 5, 6, 7. Okay. Let's just go ahead and make them all negative 950. Yep. And then this will be positive 950. All right, and then negative 150. This will be 150, positive. And then what was this? Negative 750, okay, so this will be positive 750. And just to be safe, I should probably go ahead and lock them all, so I don't accidentally move them. All right, so negative 750, negative 150, and 750. Okay. Now I think we bring in that CAD model and see if everything fits. So if we look at the 3D view, we can see all our vias. Okay. Gotta find it again. Here we go. Trying to download it. There it goes. All right, give me just a sec. We appear to be running a little slow at the moment. All right. Oh, we got to add a 3D object, don't we? I'm actually a little tired today. Watch this be the wrong CAD model too. That'd be really funny. Nope, there it is. Way off to the side for some reason. Let's see what it looks like. It might be turned. Yep. So we need to rotate around X, 90, and around Z. Wait, that's Y. Yep. So Z, 90 as well. Okay. So X, 90. Z is 90. Now it's over here. Ah, well, I got the Z part right, but the X part I definitely did not. All right, so 270 on that. Okay. Getting there. Didn't think there was any chance it was going to show us like the pin numbers or anything. So I'm going to have to make that part up on my own. Oh. Oh wait, maybe it does. Looks like there is a 1. I'm looking at the render. Oh no, not useful actually. Okay, well. So now we need to offset by some amount. Hold on. It seems to... Wow, this is actually like a really weird spot. I wanted to say halfway up this major section, but it's not. It's just like random. All right, let's get it in the middle first, then, and we can move it up. Okay, hold on 2 seconds. Height. Maybe it's from the middle of the height to H, 1.83. So half of that should be 0.92915. Let's see how far off that gets us. Oh, not quite there yet. Okay. Let's just go for 1,000 then. Let's go a little farther. $1,200 it is. Starting to get there. Okay. All right, X needs to go up probably 200 mils. So we say, no, not X, Y, sorry. Let's just say 3,300. Doesn't seem right, but It's definitely closer. All right, those pins seem to be right in the middle. So what's the thickness? 45 mils. So back up half that. Let's back up 25 or 20. 280. Closer. I don't like this walking things in, you know, to try and get them in the right spot, but there's not really a better option right now. Okay. Then we need to bring it over like 10 mils. So let's do 75, 1575. That's pretty close. Okay, maybe not. Did I mess up the spacing? Because that's possible. Oh yeah, definitely messed up the spacing. Not really sure what I did wrong there though. There is a slight difference though. Hold on. It's at 150. It should be 600 away from the top one. 750. It is 600 mils away. So unless they really messed up their model. Give me just a second. Downloading a data sheet for this part. Oh man, it's opening up in Microsoft Edge. All right, that was useless. So as far as I can tell, I have the right spacing here. So what's the best way to handle this? Also, I don't think I appreciate just how like massive this thing is going to be. Hmm. It's so weird. Let me go to their website and see. Maybe this company, like, if I download the CAD model from their website, maybe it's different or something. All right, their website has the same. Wait, am I even on the right website? Oh, yeah. Oh, I can't download the CAD unless I make an account or something. They have a symbol and footprint download, but there's not really a format that I can open in this. Hmm. Well, I'm trying to figure it out. Not having much luck, obviously. I got the X distance correct. Don't know why there's such an issue with the Y one. I think because already I can see like how there's a bit of an issue with the hole size anyway. I think what I'm going to do is just make this obnoxiously, like make each of the vias obnoxiously bigger anyway, and then go from there. Can always overuse the solder. All right, that seems like a good plan. So let's zoom in, see where this edge is at. One 1490, negative 1490. And where's this at? Positive 1510. So it is exactly 3 inches is what it's saying. I don't know where the reference point is though. So I need to basically move it so that this bottom edge is right on 1500. Which means it has to go down. So negative on the Y. Looks like 10 mils. Maybe 11. There we go. And as far as the X, how wide is this thing according to the data sheet? Width W 2.5. So 1.25 is right where we want to be at. So right there. So we need to go positive on the X, like 12 or 13 mils. $87. All right, that puts it pretty close. So that centers this thing pretty good. I think that's 1260, 1250. Where's the side? I should be at negative 1250. It is, but the other one's a little too far, so it needs to go back 5 mils. All right, that works. So now, if I look at the 3D model, we're about as close as we're gonna get. So now if I just increase the size, let's see, each one of these is 45 mils thick. We're like clipping it a little bit. I don't know. Let's add, there's 60 already. Just make them 100. Just go overkill. And make these like 150. Maybe 200. Like I said, I just want to accidentally have too much. There we go. And then if I look at this view again, this one, it fits in there anyway, even though it's kind of a little off. All right, that works. So all the vias are 200 mils in plating and 100 for the hole. Let me know how your Thursday's going. Hopefully everyone's having a good day. Excuse me. All right. Now we just have to number them all. It's 3, 4, 6, 7, 9, 10, and 12. There we go. And then we probably need some sort of marker for, probably need to draw a line around the outside of this and then put a marker. I want this on the top overlay. I'll just do the outer edge here. A few mils outside of where it's actually going to be. go, and then we need some sort of marker to denote pin 1. We'll just say 1, and we'll make this big. And a 20 mil stroke. There we go. All right. Save that. That's saved to save everything here. And then save it to the server. No! What happened? Missing pin designator in sequence. Oh, okay, that's not an issue. That error always kind of annoyed me anyway. All right, and then we get to place this part. Here it is, our transformer. I get to drop this in. Awesome. Awesome, awesome, awesome. Okay. So we can go ahead and wire these up. Let's just move it over. Actually, let's just, yeah, keep them separate. I'm not sure that's totally the best way to do this, so. All right. And then that should go to the ground. I'm assuming the ground that we're going to use for everything, so we'll see. Still not totally sure how all that works. All right, ACL. ACN. All right, and then down here. It always kind of references these other ones as the polarity. I'm trying to decide. Polarity doesn't matter as long as we make sure they're the same. So this is, oops. So this will be ACL, and this will be ACN. Okay. And then we know that these have to be connected in series because we need a full 28 volts. And then this one will be, let's see. Whoops. I need names. AC 28 L and AC 28 N. Obviously not connected to anything yet. I'm actually going to bring this out so it's a little more obvious. What's going on there? Okay. So in theory, that will make 28 volts for us. And be able to supply up to 2 amps. Okay. Next, diodes. Oh, you might be able to just buy these in a pack. I can't decide if I should do that or if I should just like, because it may not be as much fun. Bridge rectifier. Is that what that's called? Hold on. In stock, active. Interesting stuff. Bucket is an option. I didn't know you could buy stuff in buckets. Well, these are high voltage stuff too, so they're designed to do exactly this thing that I'm thinking about. It's 25 amps. Rochester, 307 minimum quantity. I need a minimum quantity of 1. Service mount through hole. And then bag, box, cut tape, strip, tray tube. Maybe we take box off of this because it looks like every box is a bulk buy thing. I don't want digireels. Ah. I kind of want a through hole part like this, but price-wise it's tricky. Ugh. 1 kilovolt, 4 amps. Jeez. Don't need anything near that bad. Let's say 200 or less. Maybe this will help us get cheaper parts. There we go. More into what we're looking for. Let's just do through hole. I forgot that I'd only... Ugh, solid markings from everything. Need more than an amp. With the whole 2 amp thing, probably more actually. I should probably go for like 4. Let's see what that gives me. It did not. 50 amps, jeez. It's gonna be an intense piece of hardware. Alright, so now it's getting hard to find something because we've got our stuff really dialed in. Oh, shoot. At least 100 or 200. Diodes Incorporated. Diodes Incorporated. They're always usually a pretty good choice. I've worked with their stuff before and it seems pretty good. This one's got a lot in stock. Maybe it's popular. I did all this assuming that this is the thing I actually want to find. It's got a screw mounting point. Okay. I think this is exactly the thing I want. So the way this is written out, it looks like it doesn't matter of the AC side which side is plugged into what, but it does matter obviously. Sorry. It does matter for the DC side, the plus minus what we do. All right, I think this part works. Once again, we'll probably have to make it, but this puts all of our diodes into a single piece, so I do like that a lot. Okay. Just trying to think through if there's anything else I need to worry about. I think we're good there. Okay. Let's see if it's available on Circuit Maker. So GBU 802. Ah. Oh, there's more letters. This is the one, right? $200 volt. I don't know what the difference between these are. Don't need that anymore. 802. Huh, don't know. All right. Well, we're going to have to make a part. Create new component. All right, we'll just make a new symbol. Can I not do... I can't do symbols to... I can't turn signals to diagonal angles. So let's see here. Best way to do this. I think just like this, actually. All right, and then line. Go, and then pins. 1, 2, 3, 4. All right. $180. There we go. Now, let's see. So the AC lines go in the middle. So mark this one L. And this one N. And I'm just going to turn the name off as well. And then this one becomes, this is the positive, I believe. The positive is the one the diode's going to it. So we're going to name this one plus. And this one minus. There we go. Okay, so how does this work? Actually, we'll get into it in just a second when we put on the schematic. Hopefully the footprint will be a little easier. I say that now, hopefully. I didn't just jinx myself there. All right, so the distance. Oh, it's giving mins and maxes for everything. Look at this. So everything is in between something. And it's all in millimeters. All right, let's go to metric. Grid. 0.5. All right. Start the pad. All right. Wow, this is actually a pretty big part. I didn't think about this. Or think this is 20 millimeters. It's almost a full inch. Man, we're using some massive components here to get all this to work. All right, well, for the size, I think 1.5 would be good, actually. Oh, no, the whole size needs to be 1.5. This needs to be closer to like 2.5 probably. Maybe 3. I always like to go overboard on this, the pad, to give it extra place to put solder and grip it. I'm gonna have to use a big soldering iron tip to heat all this up. All right, so we should go halfway between the two distances that it gives. Let me get the calculator out. So it's saying the distances between these can be either 5.33 or 4.83. So off by 0.5 millimeters. That's pretty big. I might need to have a slightly bigger hole on that. Yeah, I'm thinking 1 millimeter holes. No, it's already bigger. It's already that size. How thick is the post? 7, we did 1.5. Maybe 1.75 just to be safe. Yeah. Okay. So it's 4.83 plus 0.25. 5.08. So that's really where we want the spacing to be, 5.08 millimeters. 2.54. So negative 2.54. All right. Oh, actually, you know what? The spacing might have been spaced a very specific distance. .54 millimeters is 1/10 of an inch, so they're 2/10 of an inch apart. Yeah, 7.62. All right. This needs to be 0. And negative 7.62. Hopefully I can get a CAD model for this. All right, then I'm actually going to put symbols down to mark everything, just because that feels like it'd be a good idea. So for them, so this one's minus. L, N, M plus. All right, this will be minus. Do negative, put it right over top. Negative 7.62. And 3.5 is good, I think. One, two, three. And 2.54. And that's L. That's N. And 2.54. And that's plus. And 7.62. Okay. Perfect. So that should tell us exactly where everything goes. And plus is the notch. So I'll probably actually put something down here too. Negative 3.5. 7.62 and 1. Perfect. 3-dimensional. It's hard to see the lettering, but it is there. All right. And then we need, let's see if we can get a CAD model of this. If it loads, this link might be broken. Ugh. No 3D model available. Let's go to the Diodes Incorporated website. Maybe they have something. GBU 802. They have a SPICE model. I don't think they have any. Doesn't look like they have a CAD model though. That's disappointing. Ah, excuse me. All right, well, I think we'll have to make our own then. I'm not going to do anything crazy. I'm just going to make a big shape coming up. 18.8 plus, so it's gonna have to come up 18.8 plus 2.75. We can worry about that in a second though. We need to do, so we need to square 22.3, so 24. So it needs to go up to 12. No, out to 12. Well, no, 24 or 23 millimeters, so out to 11.5. So that's 10, 11.5. And then we go up to 3.56 to 3.6, so 1.8. Oh, but it's not centered. So just for clearance reasons, then we go up to 3, I guess. There we go. And then we'll offset it just a bit and go up distance L. So L is 18.8. And then standoff height is going to be 2.75. And there is our giant bridge thing. All right, perfect. So now let's save all this. Oh no. Hold on, what is this? Okay. None of these are actual issues, but maybe there's a way to fix them. it's not allowing me just to have these diodes because this is technically a pin. Yeah, okay. We can fix this. Let's just delete these. And then we'll just draw a line to each one. Oh, excuse me. And I think I missed one. This one. All right, now let's try that. That's still good. Save that. Save it to the server. Hopefully shouldn't be any issues. All right, so now I should be able to place the part. Where is it? Here it is. All right, so now we can probably look through this and see maybe how it works. Just a sec. Okay, so let's take this wire, run it here. This one goes here, and these come out the other side. One there, and one there. So this one gets connected to ground, I believe. Actually, I'm just going to drop that right there and delete this. All right. And then this is 28 volts. We should probably name this as DC 28 because this is our conversion here, okay? So basically, somehow this works. All right, so these are AC lines, right? So they're flipping back and forth. One's positive, one's negative, and the difference between them being 28 volts. So when it's positive, when this is at 28 and this is at 0 effectively, or it's probably more like plus 14, minus 14, current will flow through here, through this diode, out this way. And when this one's at 0, everything that's in ground would flow out through this, so it effectively makes it 0 volts, right? Then, when they flip the other way, when this one goes positive and this one goes negative, current's going to flow into this one, and this one is going to push 28 volts out this way. So no matter which one's on top, ground is being drawn to 0 volts, and 28 volts is getting pushed out through one of these diodes. And so effectively, even though it keeps flipping, you're always having a constant stream come out. Now, in reality, because they're moving, what effectively is happening is the voltage here is dropping down to 14 and then going back up to 28 every time. I believe that's the way that works. It might be down to 0, but anyways, there's a wave like a bouncing wave happening. And so what we'll do is we'll put a big capacitor here, and that will effectively like help stabilize that a little bit. The question is, how big of a capacitor? Bridge rectifier capacitor calculator. That sounds like a fun website. And polarity matters on this one. So So we're, okay. I'm going to use this thing as if I know what I'm doing, but I really don't. Let's try and get rid of some ads. So voltage is 28. Don't know that that's actually the thing we're trying to calculate or what we're supposed to use. Let's see. So many ads. Current delta time over delta U. Ripple voltage in V. Oh, that's probably the ripple that we want. So probably like 1. Change in time. We know it's 2 amps, and then for the change in time, it flips 60 times a second. So 1 divided by 60 equals 16 milliseconds. Let's do, I don't know, 16.6. This is going to give us some absurd value, I'm sure of it. 33.2 millifarads. Not as bad as I thought it was going to be, but I don't know if that's really realistic for us. I know we want a big can capacitor. All right, let's see what's realistic then. Whoops. All right, micro. Milli. All right. You can buy this value. It's about right here. I was going to say, can we find a common one? Nope. That shows some promise. 3.9. I think 4,700 would probably be a, yep. That's got a lot of them. How big are these things? Are we talking like super caps here? Yeah. Yeah, I don't know if this is really feasible. Through a hole. Is that an option? Wow, it is. Well, super cap does the job. They're just expensive, man. Let's drop down in size quite a bit. Let's see. We're using 47 millifarads. Let's go to 33, because I think that's going to be a common value as well. Yeah, 36 remaining. Okay. We still have through-hole mounting type. Okay, that's definitely better. Not great, but better. All right, what's our pricing look like? Okay. This looks like it'd be the easiest one to work with. 6.3 volts, though. That's not enough voltage. We need these two. So it looks like this one has to be it, right? Or should we just get one of the 50s to feel better about it? Nah, let's go with this. So this is probably just like incredibly excessive in like every way possible. I don't even know how big this thing is. All right, 333 tolerance voltage, case code. Okay. $10 millimeters apart for that, but I don't know the tolerant, like the thickness of it. I'll probably have to look down and find it. 272. Hold on. Oh, okay. Okay. Got it. The case code tells you that. So the case code, in our case, uh, voltage is 35, A05. So A05 is what we're looking for. 35 millimeters in diameter. Wow. They're not kidding. That is a super cap. All right. Well, I could definitely see myself messing this up. I just find it amazing that I even need something that big, you know? All right, we'll come back to that one. Let's look at everything massive. Oh, let's see. I need to check that calculator again, see if I even used it right. Interesting. Okay. So if you're allowed to drop farther, say like 3, then you get something smaller. You can get away with like 11, right? Let's see how expensive these are. They're definitely a lot cheaper. I might be able to get away with something like this. Let's see what the prices are for higher voltage, because I just feel better about getting something higher voltage. I suppose what I could do is I'm going to put 2 of these on there and pick this one. because of just how, like, because of the pad is always the same, and that way I can put a second one on there, like a good distance away, and add a second capacitor if necessary. This circuit board is going to be insane. All right, so same one. Go to our, at least I thought the same one. Yeah, it is, okay. So KO5 is the dimensions. So 30 millimeters. It's still 55 in length. Wow, that's intense. I like you can just buy some that are 50 millimeters in diameter for just no reason. All right. What are the chances this even is, like, exists in Altium? Or in Circuit Maker, sorry. I'm going to guess pretty low. Oh, I thought for a second when I saw the green symbols, I was like, oh, it does exist. No, it doesn't. All right, I'm trying to decide. I think I go ahead and make a symbol for it. Well, yeah, it shouldn't be. I say it shouldn't be too hard. It shouldn't be too hard, but I like to think about the fact that I'm probably also uh, like going way overboard here. Like I probably don't even need somewhere close to this big of a capacitor, but it's just, I don't know. Seems like a good idea. Okay. Oh. Urgh. I can only click on one thing at a time, apparently. Yep. Well, that's aggravating. Oh, well, we'll just do it this way. Who cares? Whatever. All right, I'm going to name one side positive, though, because this matters. Normally, I don't worry about this, but on these capacitors, it matters. Which side's positive, which side's negative. So we're going to make sure we get that right. All right, then we just need two vias. 0, oh, shoot. Actually, hold on. Electric. All right. 0, -5. Pull this drawing up again. Yep, they're 10 millimeters apart, so. All right, and then the hole size needs to be 2 millimeters. Wow, that's enormous. So we'll just make this 4. There we go. There's one. All right. Make this the positive side. And this one the negative. Okay, and then I need a circle. Oh, wrong layer. To show where this is going to be. I think I have to do 50 millimeters just to be safe. Jeez. Oh, it's over here. Radius. Okay. Oh, well, that makes me feel a little better. All right. No. I'm going to go excessive on this too. There we go. And then I need a 3D body. Is it not going to let me do a circle? Which layer does 3D body get drawn on? Is that its own outline? Is that what it is? Here, we can just do, actually we can just do a little square in the center. Well, maybe not. I might have to make a model and import it. In the meantime, I could just do like a square, I guess. Or something close to what this actually is. A very pixelated circle. That's what we're going to do. Oh, shoot. No, go back. Apparently I only get one shot at this. Wait. Oh, I've done that wrong again. All right. One last try. I got to focus. Forget it. I did it wrong again, but I'm just going to keep going. Because otherwise I'll be here all night. Maybe I can find a way to fix it. Oh, I did it wrong there too. And there. All right, let's see if we can fix this. That side that's the only one that's correct, like out of all of them. There we go. Ah, all right. And this one up here. There we go. No, still missing one. All right, I think that covers all of them. All right, and then this needs to extrude up like 50. I think is the size of that thing. Well, that's obnoxious. Ours will be the same height, but smaller. All right, let's save that to the server. Hopefully no errors. This circuit board is going to be epic because like these three components that we've used so far are just enormous, or all four of them actually, and so it's going to be huge because of that. And then all of the other like little digital stuff is going to fit into a tiny little corner or something. All right, I think we're good. All right, let's place this. 270, I think. Nope. Just want a 90. There we go. I think we decided we wanted 2 of these, right? Just in case. So I'm only going to buy 1 though, at least initially. And then if it fails, then we can get the second one. All right, we can turn off these names. There we go. All right, cool. The best part is when we turn this thing off, these are still going to hold so much charge in them that it could probably run for a while. We might want to put like a really big resistor here. Just let it slowly dissipate. Because otherwise it'll just hold charge for a long time. And that's a lot of charge to hold. All right, but we'll come back to that. So now we made it to the DC portion, so now we can start looking at doing the other stuff. So yeah. Okay. We'll put that resistor in next time, and I think we'll call it there on this particular schematic. We'll start on the next one, which will be all of the regulators and their outputs. And then after that, we'll make another schematic for all the digital stuff. I think that makes sense. All right. Well, thank you all for joining me tonight, and I will see you all on Tuesday. Later.